Okay, in 3 and 4, now we're going to look at the autoionization of water and then the pH scale, and they kind of move hand in hand here. All right, when we talk about the autoionization of water, that just is dealing with the fact that water can act as an acid or a base, and the process is known as autoionization of water. Okay, where most of water is water molecules, meaning not the right side of the equation we're going to look at here in a second, but actually just the water molecules themselves. So our process looks like this. I've got water, H2O, plus another water, H2O. One can act as an acid, one can act as a base. So I got a double-sided arrow. Okay, and I'm going to make HOH, an extra one there because one of these is going to lose to another one. Okay, and then I'm going to end up with my OH minus. Okay, so one's acting as the acid, one is acting as the base, and this is actually very rapid in both directions. And when we look at the K here, the K value for this, okay, remember it's products over reactants. Well, this is water, which is a liquid, so we're not going to include these two into the reaction. I'm just going to have the H3O plus or the H plus times the OH minus, and we're looking at again the concentrations. And the K value for this, the actual number, is 1 times 10 to the negative 14th. So if you look at that, that's a very small K, which means it has lots of reactants, which means it lies mostly to the left, which means then again that we have most of this is actually the water molecule. The nice thing about this and the whole reason we do this is that if I know an H plus concentration, I can then know an OH minus concentration. If I know the OH minus concentration, I can figure out the H plus concentration, which is going to be very nice here when we look at pH values. All right, so let's look at the pH scale. When we deal with the pH scale, we'll look at the molar concentration of H+. Okay, and when we talk about a molarity for H+, it's usually going to be very small. Since it's going to be small, we use the pH scale instead, which kind of gives the whole numbers to a very small molarity amount. And if you look at your chart there that you have in yours, and yours might be a little bit clearer than mine, it's like to the negative 10th or negative 13th or 14th or negative 2nd. So we're looking at small numbers that we would rather have as larger numbers and actually larger whole numbers usually. Okay, pH is what it sounds like. It stands for parts hydrogen. Yes, pH. How many parts of that solution are hydrogen? Okay, pH, when we talk about math-wise, is the negative log of the concentration of H+. So we talk about how many parts, we define it as actually the negative log of the H+ concentration. So when I have a pH that is very low, that means my H+ concentration is actually really, really large. They work opposites. Notice how my pH here at the top is 0, and my H+ concentration is actually 1. Okay, so the larger the H+ concentration, the lower the pH value. Now, you gotta be careful when we look at pH values. When you go from like a pH of 2 to 3, or 4 to 5, or 5 to 6, okay, you're not looking at a change of 1. You're looking at a pH change of 1, an H+ concentration of actually 10 times bigger. So if we have a pH change from 1 to 2, or from 2 to 3, or 3 to 4, whatever, that's actually going to be 10 times bigger, because we're looking at a log scale, or smaller, depending on which way you're growing. Okay, and when we look at this pH scale, and we see the other half of this pH scale deals with a pOH, that's just the parts of hydroxide. When we talked about a second ago, H+ concentration times OH minus concentration is 1 times 10 to the negative 14th. So they work hand in hand, this H+ and this OH minus. And how it actually works is that your pH plus your pOH is always going to be 14, where a pOH is going to be the negative log of your OH minus concentration. So if you know one of any of these 4 things, you can figure out the other. Okay, and again, we look at a more basic solution being something like sodium hydroxide or ammonia or bleach. We look at a more acidic solution being something like your stomach acid or pop or wine or bananas or coffee. Those are all very acidic. Okay, when we have in the middle pH, that should be something like water, and that would be distilled water. Tap water out of your sink is actually going to be a little bit more basic. Okay, and it's actually fairly basic at pH of usually around 10 or so. That's because you're having things that are more added to it. But for a normal, actual DI water, that should be 7. Okay, So let's try a couple of things here with some problems. What is the pH value when my H plus concentration equals 3.8 times 10 to the negative fourth? Well, we take our pH, we get the negative log of 3.8 times 10 to the negative fourth. Plug that in our calculator, find the negative log button, and you should see that that is 3.42. What I want you to kind of notice is that this pH is very close to what our exponent is. And that's kind of how it works. It would work to be the same if I had a pH of 1 times 10 to the negative fourth. My pH would be 4. If you had a concentration of 1 times 10 to the negative seventh, my pH would be 7. So it's this front number that kind of throws it to be a little bit different, but you're usually right around what your exponent value is. And what's the pH when your OH minus concentration is 1.9 times 10 to the negative 6? There's a couple of ways you can do this. You can figure out your POH, which would be the negative log of that number, which is going to be 1.9 times 10 to the negative 6, and we're going to get a value of 5.72. That would be a POH, though, and I would subtract 14 minus 5.72, and I would get a value of 8.28. You could also figure out your H plus concentration by using that, what we call KW, the K for the H plus times the OH minus. That K is 1 times 10 to the negative 14th. I don't know my H plus. I know that's 1.9 times 10 to the negative 6th. I get my H plus concentration, and then I could use the negative log of my H plus concentration to get that same thing. It's two sides of the same thing, and I don't care how you do it, whichever one makes more sense. Okay? Then what is the pH value, or what is the H plus concentration? My pH value is 3.76. Well, now we're looking at the opposite of a log, which is that 10 to the key on your calculator. Because the log we're looking at is a base 10, so you're going to take a 10 to the negative 3.76, and it has to be the negative, which will give me a concentration of 1.74 times 10 to the negative fourth for H plus. Okay, the last thing we're going to look at is some other P scales and a little bit about indicators. Okay, you have a chart there with some different indicators, and we have used the phenolphthalein, that second to last indicator, that changes from 8 to 10. So based on the pH, they all change different colors, whether it's an acid or whether it's a base. We did this with the acid-base titration, and we're going to do some more of these. But you can have all kinds of different indicators that'll change when the pH changes, and that's where you can then see a reaction happening a lot of times. Okay. Another P scale that we're going to look at and would be the pKw or a pKa or a pK. All that means is the negative log of whatever that is. So if I have a pKw, that means it's the negative log of my Kw, and that Kw is that 1 times 10 to the negative 14th. So if it ever says P something, like a pH, POH, pK, we're looking at pKa this chapter, that just means it's the negative log of whatever that value there is, or letter there is.